Okay, so first thing that we want to look at in 3530 would be systems of linear equations or linear systems. Okay, so what is an example of a linear system? A pretty simple example of a linear system is this over here, right? So if we're looking at this here, this x plus 2y is equal to 2, and 2x plus 2y is equal to 0, right? This is an example of a linear system, right? So this is a linear system with two equations, two equations, and in two variables over here, right? This is something you would have seen in ENGR 1180, and something this basic here you would have seen back even say in Form 4, Form 5, right? You probably didn't call it a linear system, you call it, say, simultaneous equations. Okay, right. Okay, so what we would want to do in this course, well, to start off with, is to be able to solve these systematically, right? Okay, so this is one example of a linear system. This is a linear system where you have two equations, right? And it's two equations, right? Sorry, two equations here in two variables, and the variables here are x and y. Slightly more complicated system here is this one here, right? This is, notice here what you have is three equations here, right? X, y, and z, right? And sorry, you have three variables here, right? X, y, and z, and then you have three equations. This is your first equation here. This is your second equation here, and this is your third equation here, right? Right. So here the variables are x, y, and z, right? Okay. So these examples are from the Austin textbook, the Austin Linear Algebra textbook that I posted on my 3530 website. Right. Okay, so for a next example of a system more complicated, it would be this one over here, right? Not that much more complicated. So in this case, what I have is I have four variables now, right? x1, x2, x3, and x4, right? And I have three equations here, right? First equation, second equation, third equation, right? So as I say in this example, this is a system of linear equations in four variables, right? x1, x2, x3, and x4, and three equations, right? 1, 2, 3, right? Okay, so you want to notice a small difference between this linear system over here and this linear system over here, in that here I'm calling the variables x, y, and z, right? And here the variables are x1, x2, x3, and x4, right? Okay. There's no major difference, it's just really notation, and then, well, you see past a certain point, this is four variables here, x1, x2, x3, x4, right? So if you want, you really could call this x, y, z, and probably w, right? But if you have like a really large system, what's going to happen is that eventually you're going to run out of letters of the alphabet, right? Okay, so it's easier to do it this way, right? To label your equations. First equation is x1, second equation is x2, x3, and x4, right? All right. Right. Okay, so this is, you want to notice that each of your equations here, right? There's nothing involving, say, like x squared and say like cosine x or 1 on x or anything like that, right? This is x1 to the power 1, x2 to the power 2, and also you don't have anything like a product x1 times x2, right? This is x1. Okay, so for example here, this is x1 plus a scalar multiple times x2, right? So x1 plus a scalar times x2, right? Likewise over here, scalar times x1 plus x2 plus scalar times x3 plus some scalar times x4, in which case here the scalar here is minus 7, and then you have a scalar on this side, right? And typically we're gonna write your equations in this sort of form where your variables are going to be on your left hand side, and then you just have a constant term on this right hand side. Okay, so what we will not be considering in this course would be, say, a system like this, right? So this one is okay for us, right? This is linear over here, right? But this second equation here, right, is not linear, right? You see, and you have this term in x squared, right? So this is not a system of linear equations. It's not to say that you can't solve this, right? And this one is fairly easy to solve, right? You just do it by substitution, right? And if you have more complicated ones like these with terms in x squared and say y squared and so on, there are ways to solve this. You'd probably need to start using a little bit of ring theory and so on, and try to find like a basis for ideals and etc. Right? So this would fall into commutative algebra, which is probably nice, but we're not gonna do. Right? So we don't look at cases like this over here, right? The only cases that we will look at is when your equations here are linear, right? So one more time, this is an example of a linear equation. And this equation over here is not linear, right? So we're not going to be doing things like that in this class. All right. All right. Okay. So we want to solve these linear systems that I was talking about, right? So a very simple linear system is this one over here, which is in two variables x and y, and it's two equations, right? As a next example, I have, say, a different system here, right, which again is in two equations, x1 and x2, which is in two variables, x1 and x2, and it's two equations here, right? Okay, so how will we go about, say, solving this first one over here, right? Well, what you would have known probably from your high school and so on, right? And this is the basic way of doing this is um, you solve it by substitution, right? So you see your first equation over here, you could solve for the x, right? And you see that the x is equal to 2 minus 2y, right? And then what you do is you take this x is equal to 2 minus 2y and you substitute it into your second equation over here, right? Okay, so your second equation is 2x plus 2y, and you take the 2 minus 2y and you substitute it into this, right? When you substitute into this, you get an expression purely in terms of y, which you can solve for y, right? And when you do that, what you're going to get is you're going to get y is equal to 2, right? Right, okay, and once you get y is equal to 2, right, they don't say over here, but what you do is then you need to figure out what the x is, right? So when y is equal to 2, you put y is equal to 2 into this, and you're going to get 2 minus 4, which is minus 2, right? So your answer here would be x is equal to minus 2, y is equal to 2. And you can check that, right? So when x is equal to minus 2 and y is equal to 2, you get minus 2 plus 4, which is 2, right? And when x is equal to minus 2 and y is equal to 2, you're going to get minus 4 here, plus 4 over here, which is 0, right? So what you got is you got a solution, right? And that is what we're looking for. We're looking for solutions, right? Okay, so likewise over here, I don't have the working for this one, but here I have this system, right? This again, you could probably solve by substitution and so, right? And it's not hard to see that this 3 minus 1 is a solution of this system here, right? If I put x1 is equal to 3 and x2 is equal to minus 1, this would give me 3 minus minus 1, which is plus 1, so 3 plus 1, which is 4, right? And if I put a 3 and minus 1 over here, I'm going to get 6 minus 3, which is 3, right? So this is also a solution, right? Anyway, so the point that I want to make is, well, the most basic way to solve a system over here is by substitution, right? But you can't keep doing that if you have, say, like a 3 by 3 and so on, right? If, for example, you have this 3 by 3 over here, well, you could say what you do is from these two over here, you eliminate x1, and then you use these two over here to also eliminate x1. So what you'd end up with is two equations just in x2 and x3 and x2 and x3, and then you solve that, right? Yeah, that's starting to get cumbersome, and if you have 4 variables, then it's just really too much work, right? So this business about doing substitution, so it's nice for like low-level examples, but isn't gonna really kind of carry it that far, right? Okay, so what we want is a more systematic way of uh, dealing with these systems, right? Okay, so what is a more systematic way of dealing with this? Well, what's the overall objective here, right? Okay, so let's just say use this example here, right? This is my original system, right? Okay, and somehow this is so for this example, what I have is three variables and three equations, right? Okay, so the objective over here is somehow what you're going to do is you want to transform the system, right, in a systematic way, right? You don't want to radically transform it, that you alter the solution space, right? But you're going to transform it, right? And you're transforming it until you get something that is of this sort of triangular form over here, right? Okay, so roughly this is, if you're looking at this left hand side, this would be what you'd call upper triangular, right? Because the non-zero entries are basically in this upper triangle. Anyway, all right. Okay, so once you have it in this sort of triangular form, right? Something like this is pretty easy to solve, right? Because, well, what do you do, right? You're just gonna solve this by back substitution, right? Your x3 is just literally 4 over here, so you know what that is, right? And what you could do is you take this x3 is equal to 4, right? And you put it into there, right? And when you put it into there, right, you could just solve for the x2, right? And that would give you x2 is equal to minus 3, as I have over here, right? And now I know the x1, sorry, now I know the x3 and the x2, and I can figure out what the x1 is, right? So the x2 is minus 3, right? The x3 is equal to 4, right? So what does that give me? That gives me minus 6 over here, right? That gives me 8 over here, right? Yes, right? So I have minus 6 over here, I have 8 over here, so overall this constant here works out to be 2, right? So I'd have x1 plus 2 is equal to 4. And I can take this 2 and move it across, and I get x1 is equal to 2, right? Okay, so something like this. This is essentially when we're doing solving a system of linear equations, and we will, I mean, I think you have an idea, you know where I'm headed, right? I'm going to be using row reduction to solve this, right? Which is the row reduction technique that you would have seen from 1180, right? But right, the idea here is that eventually what you're looking for is part of any algorithm that we're going to use, right? Is you're going to first get it into something that is upper triangular like this, and then effectively use back substitution, right? But the algorithm that we would use, while it incorporates this sort of idea, right? You probably not really gonna see it, right? But you want to bear in mind that this is basically what we're doing in that algorithm, right? When we solve it. All right. Okay. So let's see if I could explain what how we go about solving by a method that is not this substitution, right? So this sort of more systematic way that I'm talking about, right? Right. Okay, so I have, this is the equation here, 2 by 2 equation here that I solved earlier on via substitution. Right. Okay, so this 2 by 2 system over here, solved by substitution, right? And now what we want to do is we want to do it in a different way, right? So this is the textbook which I have posted on the website, right? Okay, so I want to do this in, as I say, in some sort of systematic way, right? So what's the goal over here, right? The goal over here is you want your system over here, right? This is the system that I have, the original system, and I transform it into something that is triangular like this, right? And once it's triangular like this, I can solve, right? Because this one, this you're going to do by the back substitution, as I just mentioned, right? Here, what you'd get is you'd get that y is equal to 2. And when you put y is equal to 2 into this over here, then you can figure out what the x is, and that will give you x is equal to minus 2, right? So how do we go from here, this system over here, to this system over here, right? Okay, and how you do it is you eliminating this variable x over here, right? So what you do is you take, and in order to eliminate, sorry, well, when you want to eliminate this 2x over here, right? So notice when you go in from this system here to this one over here, the first one is the same, right? So this equation here is the same as this equation here, but your second equation over here has changed, right? But it's changed in some sort of systematic way, and by systematic, your solution set isn't going to be altered by the method that we're using, right? Okay, so how do I get rid of this 2x, right? Well, what you do is you consider this equation, this top equation over here, right? And what you're doing is you're multiplying it by minus 2, right? Okay, so when I multiply this top equation here by minus 2, I get this minus 2x minus 4y is equal to minus 4, right? So minus 2x minus 4y is equal to minus 4, right? And then what you're doing is you're taking this equation and you're adding it to your second equation, right? So the minus 2x minus 4 is minus 2x minus 4y is equal to minus 4. You add it to your second equation, and when you add it to your second equation, what happens is the minus 2x over here will cancel with the 2x, and this over here minus 4y plus the 2y will give you minus 2y, minus 4 and minus 4, right? Okay, so what you're doing is, if you want, you add in this equation to this equation, right? And by adding the equation means that you add all terms, you add the corresponding x terms, you add the corresponding y terms, and you add the corresponding constant terms, okay? Okay, and well, how do I know to use, okay, so I had x plus 2y is equal to 2, right? How do I know to multiply this equation here by minus 2? So how do I know this x plus 2y is equal to 2? How do I know to multiply it by minus 2? Well, how you know that is because what you want is you want to eliminate this 2x over here, right? And if you're going to eliminate this 2x, what you'd need is a minus 2x over here, right? So what you're doing is you're looking at the coefficient of this x here, which is 1, right? And you need to multiply that by minus 2 in order to get this minus 2x, right? Once you have that minus 2x over here in this equation, when you add, the x term would go away and you have minus 2y is equal to 0, right? So that actually is one of the key ideas when we transform in a system, right? Okay, so this system over here, I multiply this equation throughout by minus 2, in which case I get minus 2x minus 4y is equal to 4. And then I add it to this here, right? Notice I didn't really change this first equation, right? All I'm doing is I'm just taking a multiple of this one and adding it to the second one, right? And when I do that, I get minus 2y is equal to minus 4. And now this is in a triangular form, and this is easy to solve, right? You just do your back substitution. All right. Okay, so as a next example, more complicated example of eliminating the variables using these adding and subtracting of equations, right? And this sort of adding and subtracting of equations, these are called equation operations, right? I will explain what those are in more detail in a while, right? Okay, so I have, this is my original system over here, right? Okay, what I want to do is I want to start eliminating the variables over here, right? And I do that in a systematic way, right? So I'm going to change my equations. Notice here what they did is they took this x over here and they got rid of the x, the 2x term below it, right? So it's the same thing over here, right? With this x1 over here, what I want to do is I want to first eliminate this x1 here, and then I want to eliminate the 2x1 over here, right? And once I'm done with that, what I'm going to do is I'm going to move across in the next column and see if I can get rid of some of the x2s and so on, right? Okay, so idea is first get rid of this x1, right? And then get rid of this 2x1, right? Okay, so how am I going to get rid of this x1 here on this second equation, right? How I'm going to do it is I'm going to take this equation over here, multiply it throughout by -1, and then add to this, right? Okay, and when I multiply it throughout by -1, I'm going to have minus x1 here, right? Minus 2x2, minus 2x2, minus 2x3, and minus 4, right? Okay, so when I add, I will have 0 here. I will have 1 here, I will have 1 here, and then I'll have 1 here, right? And that is what I get here, right? When I add, so -1 times equation 1, when I added it to equation 2, I got 0 here, 1 here, 1 here, and then a 1 constant term, right? Notice I left this 0 here, right? Instead of just dropping it off as an x1, right? I did that for a reason, right? Which I'll get to, right? Okay, so I got rid of one x1 over here, right? And now what I want to do is I want to get rid of this this 2x1, right, in the third equation, right? Okay, now how would I do it? I'm still gonna use your first equation here, right? What I do is I multiply this now because I want to get rid of 2x1 over here. Now I multiply by -2, right? And when I multiply by minus this equation here by -2, I have -2 here. Minus 4x1, minus 4x3, and then -8, right? Okay, so when I add, this will give me 0. This is -4 plus the 6 would give me 2. This is -4 plus the 5 would give me the 1. And this is -8 plus the 6, which would give me -2, right? Okay, so I'm doing well so far, right? I got rid of the x1 terms. Okay, notice I still have this x1, but everything below it is 0, right? And now what I do is I now move to my second column, and I start working on the x2, right? Now, when you see you can't get rid of your variables altogether, right? And the next thing too is you're heading towards a kind of triangular form over here, right? And because this is essentially what you want, this triangular form, right? What you're going to do for this x2 over here is just eliminate. All you need to do is eliminate the one below it, right? You can, if you want, eliminate the one above, and we will get to that eventually. But for the time being, we're just looking for trying to get this triangular form, right? Okay, so now what I want to do is I want to get rid of this 2x2, right? Now how would I do it? Now I take my second equation here, right? And I multiply throughout by -2, so I'd have a -2 here, -2 here, and a -2 here, right? And then I add, right? So when I add, I'll get a 0 here. I will get -2 plus 1, which is -1, and then I'll get -2 plus -2, which is -4, right? So I get this. All right. And then that actually is my triangular form. I can clean it up a little bit. Here I have -1 x3 here, right? And what I want to do is it's nice to have the coefficients in front of these pivot variables. You have them positive, right? So I multiply this equation throughout by -1, and I get x3 is equal to 4, right? Now I left these zeros here to compare it to a next solution later on, right? But now what we could do is 0 times x1 is 0, right? And 0 times x1 and 0 times x1 is 0, right? So that's just 0, right? So 0 plus this expression, I could just write it as x2 plus x3 is equal to 1. And here, this expression here, I can just write it as x3 is equal to x4, right? And now over here, we could back substitute, right? And I think I did this for you already, right? So to get your solution here, you back substitute, right? So the point is, what you did is you started with your original equation over here, right? Original system of equations here, right? And you took a multiple of this equation and added it to your second equation to get rid of this x1, right? Then you took a multiple of this equation over here and added it to this third equation over here to get rid of this 2x1, right? And then when you are done with that, right, you got this, right? And then next thing too is now what you want to do is get rid of this 2x2. So you took a multiple of this over here and added it to your third equation, and that got rid of this this third x2 over here, right? the x2 in your third equation, right? Once you had that, you just cleaned it up a little bit and you got this, and now this you could solve, right? So this is basically the method that we're going to use to solve linear systems in this class, right? What we don't want to do is, eventually what we're going to do is you're going to drop off the x1s and the x2s and so on, right? And you're just going to keep the coefficients. And by dropping off the variables x1, x2, and x3 and so on, right? But still being able to solve, right? Okay, so I have the same system that I was just talking about here, right? Okay, and I did use equation operations to eliminate this, for example, here to eliminate the x1, and then to eliminate your second x1 here, right? And then finally to eliminate this x2, right? Okay, now, well, let's just, so this is my first, this is my original system over here, and what did I do, right? What I did is I multiplied throughout over here by -1, and I added it to this, right? Now, I multiplied by -1, right? And when I multiplied by -1, I got a -1 here, I got a -2 here, -4 there, right? So when you add, you're going to get a 0 here, you get a 1 here, you're going to get a 1 here, and then you're going to get a 1 here, right? Which is this, right? 0, 1, 1, 1, right? Now, what you want to notice is when you did that, right? And I kept the 0 over here, right? Notice the position of the x1, x2, and x3 isn't changing, right? You have an x1, x2, x3 over here, and x1, x2, x3 over here, right? So those are like, if you want, the little placeholders or little boxes, right? But the main thing over here is that you want to keep track of your coefficients, right? So if you can keep track of your coefficients in a systematic way, right? When you're doing these equation operations, then it turns out that you don't really need the x1, the x2, and the x3 anymore, right? You could just drop them off, and you just somehow want to remember that they're still there, right? Okay, so that is what's done over here when we start using matrices to represent the system, right? I will come back to this, and I will, because I'll need to probably just explain a little bit as to what exactly augmented matrices are, so on, right? But this is just to give you an idea of overall where we're heading, right? Okay, so you have your system over here, right? So what you do is with your system, this is, and it's the same system here, right? What you do is you just write out the coefficients, right? So you have 1, 2, 2, 4 here, and you have 1, 2, 2, 4 here, right? And you have 1, 3, 3, 5 here, and 1, 3, 3, 5 here, right? Okay, notice you use a little line over here to separate these coefficients. These numbers over here are different. If you want the behaving, they carry a different meaning than the constant term over here, right? So you have a line over here. And the line over here is to indicate that these guys over here are just constants on the right hand side, and these over here are coming from the left hand side. Or if you want, for this line over here, this is your left hand side and this is your right hand side, right? Okay, so what did we do, right? What we did is, first thing is we got rid of this x1 by multiplying throughout over here by -1, right? So you took -1 times this equation and then you added it to the second equation, right? And that's what I'm going to do over here, right? I'm going to take -1 times this row and add it to the second row, right? So I'm doing essentially the same thing, right? And I have this little notation over here, right? Minus row 1 plus row 2, right? When I do that, I'll get a 0 here. I get, remember what I did? -1 times this added to this. So I get a 0 here, get a 1 here, 1 here, and a 1 here, right? So I'm doing the same thing. It's -1 times this over here added to this, right? With the idea being that you want to eliminate this x1, right? But now what I'm doing is I'm no longer carrying along the x1, the x2, and the x3, right? Because I don't really need them, right? I know, for example, that this here, this is 2x2, this means 2x2, and this means 3x2, and so on, right? And this means 5x3, right? So if I don't need them, I could just drop them off, and it's just too much to write, okay? And you just use the coefficients themselves, right? And the coefficients themselves, when organized in this way, they form a matrix, right? And this is one aspect of using matrices, right? So what you're doing is you have the system over here and you're organizing the information for the system into a matrix, right? So that is one reason why matrices exist, right? They exist to organize information for you in a systematic sort of way, right? Okay, right. So eliminate, take -1 of this equation, add it to this one, so that corresponds to taking -1 over here and adding it to your second row, so I get the 0 over here, right? And notice over here, what did I do over here, right? What I did is I took -2 times, so that got rid of this x1 here. Now what I want to do is want to get rid of this over here. So you want to get rid of this 2, right? So what you do is you take -2 times this first row and add it to your second row here, right? Okay, and you get this. So now this, you got a 0 over here. In other words, the x1 is gone over here, and now you keep going, right? So next thing now is, once you got to this point, what you wanted to do is eliminate this x2, and that's what I'm doing over here, right? I want to eliminate this 2 over here. So how did I eliminate this 2x2? What I did is I multiplied this equation by -2 and added it to this one, right? And that's what I do over here, right? -2 times this equation, and I add it to row 3, right? So I got a 0 here, right? I got a -1 here, and I got a -4, right? So I get this, which corresponds to this. So if you compare, right, the coefficients over here for all of these, it's the same as a corresponding coefficients for these matrices over here, right? Okay, and then finally I get to this, right? And this here, right? Remember, these values are these are coefficients of the of a system, right? So what you could do is, if at this point in time, you could actually put them back, right? So you can put them back. This is x1 plus 2x2 plus 2x3 is equal to 4, right? This is x2 plus x3 is equal to 1, right? And this is x3 is equal to 4, right? So you get this, and that is really what we had from before, right? Okay, so the idea here is this method that I had of systematically eliminating the variables here, right, to get this kind of triangular form. I can do it this way, right? Where I'm doing the same thing. The only thing is I just not writing the x1, x2, and x3, right? So if you have your system, first thing you do is you form your matrix of coefficients. Here, this is called an augmented matrix, right? And then you systematically eliminate the values, right? And notice how you're doing it, right? You start with this top entry over here, and you eliminate everything below it, right? And then you jump to your second column, right? Once you eliminated everything below it, make it 0, right? You jump to your second column over here, and then you don't start with this one, you start with this one below it, right? If you did start, you say that you wanted to start with this one, that's not good, right? Because if you tried to use this over here to eliminate this 2, right, what would happen is this 1 over here would come down and mess up things, right? I would put back this 1 over here would come back and give you something that is non-zero here, right? So that's why you start with 1 below, right? You start with 1 below over here, and then you use that to get rid of this one, right? And then once you get this sort of triangular pattern, this is pretty much what you're looking for, right? You clean it up a little bit with the getting rid of this negative sign by multiplying through it by -1 to get this over here. And then once you have this augmented matrix, this corresponds to a system, right? So you could put back the x1, x2, and x3 and so on to get the system. And the point is, this system over here and this system over here, you didn't lose any information, right? And that takes a little bit of justification, but you didn't lose any information. So the solutions that you had from this over here, it's exactly the same solutions that you have for this, right? So you could use this and solve this, and when you solve this, and this is easy to solve because it's triangular, right? Once you solve this, it means you get the solution for this one on top here, right? Okay, so we considered this system of linear equations. System is in 3 variables, x1, x2, and x3, and you have 3 equations over here, right? Right, so a formal definition of what a system of linear equations. This is an example of a system of linear equations, and your formal definition is just saying that system of linear equations, it's going to be a collection of m equations, right? So in this case, the m is equal to 3 equations in variables x1 to xn, right? And here, this system of linear equations is in variable x1, x2, and x3, right? So the n in this case is n is equal to 3, right? So by small n over here, n is the number of variables, right? It's a system of linear equations if it's in this form, right? So a constant times first variable, constant times second variable, up to constant times nth variable, and it's equal to some constant, right? So you want to notice that this is in exactly that form: constant times first variable, constant times second variable, constant times third variable, where the n is equal to 3 is equal to a constant, right? And all of your equations need to take that form, right? Your coefficients here are constants. Right? The small a's over here are constants, and for us it's going to be real constants, right? You can use complex valued constants, and that's something that you would probably want to do, seeing that most of you all are from electrical, right? Because you'd want to solve, say, a system with, say, like a complex impedance or something like that, right? Right, okay, but in this class, we're going to restrict to the case where these constants here are reals, right? So we're pretty much not really going to deal with any complex values in this course, right? Yes. All right, okay, so right, so this is a definition of a linear system, and well, what does it mean for something to be a solution, right? Okay, so for example, this over here, 2 minus 3, 4, right? 2 minus 3, 4 is a solution of the system, right? If I put 2 in here and minus 3 here and 4 over here, well, what do I get? I'll get 2 over here, right? Minus 6 plus 8, right? Which should be 2 plus 2, which is equal to 4, right? And if you put it into all the equations, well, I guess we could do that, right? So 2 times 2 plus minus 3, which is minus 9, right? So this is going to be minus 7 here, and then plus 3 times 4, which is 12, right? So minus 7 plus 12, which is 5, right? And then 2 minus 3, 4, right? You're going to have, right, a 4 over here. You're going to have a minus 18 over here, when 6 times minus 3, so 4 plus minus 18 is 14, so I have 14 here so far. And this is, sorry, I have minus 14 so far. Okay, so from the top, right, 2 minus 3, 4, right? So 4 over here, right, minus 18, which is minus 14, and this x3 is 4, so that's 20. And 20 minus 14 is 6, right? So when I put in 2 minus 3, 4 for each equation, right, it satisfies each equation, okay? So that is what a solution is, right? This S1, S2, S up to Sn means, so this is just a vector consistent of scalars over here. It means that if I put S1 in for x1, S2 in for x2, and so on, Sn for xn, right? And I work out this left-hand side, it's equal to the right-hand side, and that's true for all equations, right? So, and that's exactly what I just did for the two. So in this case, the S1, S2, and S3 would be S1 is 2, the S2 is minus 3, and the S3 is 4. And when I put these in, the 2 minus 3, 4, I put it into here, here, and here, I get 4, right? Put it into here, here, and here, I get 5. Put it into here, here, and here, I get 6, right? So this 2 minus 3, 4 satisfies each of the equations, which means it's a solution, right? That's nothing new. I think you know what a solution is for a linear system, right? Your set of all possible solutions is called a solution set, right? In this particular case, we have a unique solution, right? And you've probably heard or you know from 1180 that you have 3 cases where you're going to have either a unique solution for linear system, no solutions, or an infinite number of solutions, right? So this is the case of where you have a unique solution, right? The collection of all possible solutions of a linear system is called a solution set, right? Okay, so this over here is a solution, right? And your set of all possible solutions would be for this system over here, set of all, because you only have a unique solution, set of possible solutions would be 2 minus 3, 4, right? So in this set over here, you only have one element, and this would be how you'd write a solution set, right? You could write it like 2 minus 3, 4, but technically is not correct, right? So that's not a set, right? You write it like that, you lose some marks on your exam, right? So you want to write it correctly. It's going to be 2 minus 3, 4, and then you need to put your curly brackets to indicate that it's a set, right? Okay, so let's look at a next system which is a little more complicated. This one over here, right? So this is a linear system here, right? Using a notation or definition over here, right? This is, you have the number of equations, m equations, the number of equations m is equal to 3, right? 1, 2, 3 equations. And you have 1, 2, 3. Okay, so so remember labeling for the variables x1 to xn, right? And in this case, the variables are x1, x2, x3, up to x4, right? So we have n is equal to 4 variables, right? Now, this notation where we have m is equal to 3 and n is equal to 4, right? You probably you want to remember this because this is something we're going to use throughout the course, right? So when m is the number of equations and n, we're going to use small n as the number of variables. Anyway, so this is in system in 3 equations and n is equal to 4 variables, right? Okay, now because your number of variables is more than the number of equations, right? Remember I said that you have 3 possible cases: unique, solution, no solution, and infinitely many solutions. Right. Once you have more variables than equations, right? You can no longer have a unique solution, right? So the only possibilities no solution whatsoever, or infinitely many solutions, right? And in this case, right? I know you'll work out this right later on, right? This linear system over here has infinitely many equations, right? And how you would write your solution set like this is you write it in this way over here, right? Okay, and you'll see later on how you do that, right? But notice it's in set notation over here, right? As how this one is in set notation, which are curly brackets like this. This one is in set notation, but it's a little more complicated, right? Okay, but the key thing, each okay, so for this set over here, right? What do you want to notice? What this means is that it's this vector plus s times this vector plus s time plus t times this vector, right? Where by vector I mean like this over here. This vector of 4 elements is a solution, right? Where x1 is equal to minus 2, x2 is equal to 4, and so on, right? Okay, so each vector of size 4 inside over here is going to be a solution, right? And the point is that if each value of s and t, I will get a different vector of length 4, right? So for example, if I choose s is equal to 0 and t is equal to 0, what I will get is I'll simply get this vector over here, minus 1, 4, 0, 0. And this minus 1, 4, 0, 0 is in fact a solution of the system, right? And you can check, right? So let's check it, right? If I put minus 1 and 4 in over here, right, what I'll get is minus 1 plus 8 over here, which gives me the 7. Right? If I put minus 1 and 4 in over here, I'm going to get minus 1 plus 4, which is 3 over here. And if I put minus 1 and 4 in over here, I'm going to get minus 3 plus 4, which is 1 over here, right? Everything else, these x3s and x4s are all 0, right? So this minus 1, 4, 0, 0 is a solution of this system here, right? If I use a next value of next, okay, so that actually is this minus 1, 4, 0, 0 is what I got by using s is equal to 0 and t is equal to 0, right? If I decide that I want to use, say, different values, so for example, what I'll do is I will use s is equal to minus a half, right? Okay. Right. Okay, so if I use s is equal to minus a half over here, right? And I'll use s is equal to minus a half, and I'll use t is equal to 0, right? Okay, so why I'm using s is equal to minus a half is when I take this minus a half and I multiply it by minus 2, 1, 1, 0, right? I'm going to get 1 minus a half, 0, right? And why I'm doing that is when I get a 1 over here, right? That when I add to minus 1 over here would give me 0, right? So why I'm doing all of that is I want to put in something relatively simple. This is a solution, right? But I don't want to use this over here, and I don't want to use this over here because it's just going to be too, it's a little too tedious to check, to put in this over here and to check this, well, verbally, right? So choosing a value that's a little more reasonable. So if I choose s is equal to minus a half over here, and I choose t is equal to 0, what I will get is when I add it up, right? So the minus a quarter, 0, 0 times half times this over here. Now half times the minus 2, 1, 1, 0 gives me this. So this vector, half over here, 0 over here, gives me this. And when I work this out, I will get 0, 7 on 2 minus a half, 0, right? And I'm saying that this is also a solution, right? And I can check, right? Let's check, right? So I have x1 is equal to 0, right? The x2 is equal to 7 on 2, and then the x4 is equal to 0. So I'm going to get 2 times 7 on 2, which is 7, right? Okay, over here, this is going to, if I put in the same thing, I'm going to get a 0 here. I'll get a 7 on 2 over here, right? I'm going to get minus a half. So 7 on 2 minus a half is 6 on 2, right? And 6 on 2 is 3, which is this here, right? And then when I put in 0, 7 on 2 minus a half and 0, right? I will get 0 here. I get 7 on 2, right? Minus 5 on 2, which is 2 on 2, which is 1, right? And this is 0 over here, so I have 1 plus 0, which is equal to 1, right? So we see that this also is a solution, right? So we just checked that both minus 1, 4, 0, 0 is a solution, and this over here is also a solution, right? It satisfies all three equations, right? Now that was using s is equal to minus a half and t is equal to 0, right? I can use anything, right? I can use 1 over here, I can use 0 here, I can use 0 here, I can use 1 here, I can use half here, half there, which means, and all of those would be solutions. So for any value of s and t, I get a solution. And that basically, well, that really means that this here is an infinite set, right? A set with an infinite amount of elements, right? And all of them are solutions. So that would be how you'd write an infinite solution set, and that's how we do it in this class, right? In this sort of, using this sort of notation here, right? And you'll see when we solve our systems, we can naturally get the solution in this form, right? And we will do that later. Right, okay, so let's consider a definition of two systems of linear equations being equivalent, right? So two systems of linear equations are equivalent if your solution sets, the solution set for each one is the same, right? If they're equal, right? Okay, so consider, say, this system over here, right? This is a 2 by 2 system, right? Okay, and 3 minus 1 is a solution, right? If you try substituting the 3 minus 1 into here and here, you'll get 4. And likewise over here, you'll get 3 over here, right? Okay, so this is a solution here. And also you can check that 3 minus 1 is a solution of the system over here, right? Right, so this is one system and this is a different system, right? Now if you're looking at this system over here and you're looking at this system over here, right? You want to notice that the first equation and both of them are the same, and the second equation, well, the difference between the second equation here and the second equation over here is really you took this equation over here and you multiplied it throughout by 2, right? Right. Now, okay, so if you, let's just focus on the second equation over here and the second equation over here, right? Now, if 3 minus 1 is a solution of this, right? When I multiply throughout by, so if I have the 3 over here and the minus 1 over here, and if I multiply everything by 2, right? That actually doesn't change the fact that 3 minus 1 is a solution, right? Because you could think of it this way, right? If this satisfies, you have 3 over here and you have minus 1 over here. So 3 minus minus 1 is going to give you the 4, right? And you multiply throughout here by 2, right? You're going to get 2 times the 3, 2 times the minus 1, right? And then the 8, right? And everything will still be equal again, right? So if the 3 minus, if this is a solution over here, it's going to be a solution over here, right? So multiplying an equation by a scalar, right, doesn't actually change what the possible solutions are, right? So well, that's the idea of it. This is a pretty basic system over here, but anyway, so the reason why this system over here is equivalent to this system over here is really because you just multiplied one equation throughout by a positive scalar, and when you did that, you didn't really change anything, right? Okay, so what I'm doing here is I'm modifying the equation, right? I'm modifying this equation and I'm changing it to this equation over here, right? And that is an example of what I call an equation operation, right? And you have 3 types of equation operations, where the second type is where you can multiply one equation by a non-zero quantity, right? So if you have a system, given a system, right? Given a system like this, an equation operation is what you're doing is you're modifying the system in some sort of consistent way, right? And one equation operation is multiplying throughout by a non-zero scalar, right? So for example, over here, I multiply throughout by a non-zero scalar, right? Once you do this equation operation, you don't change the solution set, right? Okay, so going from here to here, right? Both of these have the same solution set, right? And in a way, at least for this case over here, when you're multiplying by a non-zero scalar, right? It's sort of common sense, right? Because if something is a solution for this here, right? Right, with the 3 minus 1, if I multiply throughout by say like the 2 over here, it doesn't change the fact, it doesn't change the solutions for this equation, right? And for the overall system. Okay. Right. Okay. Your second type of equation operation is when you switch the location of swap the location of 2 equations, right? Okay, so consider this is my original system over here. I wrote it here, right? And this is when I swap 2 equations, right? So this is my original system, and I get a new system where I swap 2 equations, right? Now, if you think about what the solutions, this 3 minus 1 is a solution of your the system over here, right? We checked that already, right? And you put in your 3, put in your minus 1, 3 minus minus 1 gives you 4, and so, right? So the 3 minus 1 satisfies this, and the 3 minus 1 satisfies this. If you change the order of the equations, that doesn't change the fact that the 3 minus 1 satisfies this one and satisfies this one, right? Clearly, right? Rearranging the equations doesn't change that over there, right? And it may not seem sort of clear as to why you'd want to rearrange the equations here, right? This is usually there's no we don't really need to do it that much. Chances are, if we using these equation operations, right, what we're going to do is you're more likely going to use 2 and 3, right? You do use 1 once in a while, right? That's to sort of put your system in a nice form, right? Okay, but you see that, okay, so one more time, this is my original system, and I do an equation operation. In other words, I modified system by by changing the order, right, of 2 equations, and that doesn't change the solution set, right? Okay, so this system over here and this system over here are equivalent, right? Okay, so your last type of the 3 types of equation operations that we have over here is when you multiply each term of equation by some quantity and add it to a second equation, right? And we've actually been using that already, right? We did that already. Okay, so for example, we had this original system over here, right? We looked at this example. And what I wanted to do is, what I did is I eliminated this x1 first of all, right? And how I did that is I took this equation here, multiplied throughout by a non-zero scalar, and then added it to this one, right? So take this equation, multiply throughout by -1, right? So I get a -1 here, -2, -2, and -4. And when I add it over here, I get 0, 1, 1, and 1, right? Which is this, right? So I multiplied an equation, first equation by -1 and added to the second equation, right? And this is an example of doing this over here, 3, right? Okay, and it turns out that this here and this here has exactly the same solutions, right? And that can be proved right? That can be proved, right? It's not proved in the proof isn't stated in this over here, right? Okay, and it's you can think about it, and if you think about it a bit, you realize that it makes sense, right? But it would require some proof, right? Anyway, so your solution, the solution set doesn't change when you apply an equation operation of this third type, right? In other words, when you add a multiple of one equation to the next equation, right? Okay, so what I've been saying is that okay, so for example, if you swap 2 equations in a set, if you have a system over here and you swap 2 equations, you don't change the solutions, right? If you have a system over here and you multiply one equation by a non-zero scalar, you don't change solutions, right? So that's 1 or 2, right? And if you have an equation and you add a multiple of this equation to a second equation like this, you don't change the solution set, right? So that is what this theorem is saying over here, right? It's saying that when you do these types of operations, you don't change the solution sets, right? You don't change things, right? Okay, right. So why do you care about the equation operations and the fact that it doesn't change the solution sets, right? So over here for each of these, right? What I was doing to go from here to here, I added a multiple of one equation to the next equation. Likewise, from here to here, I did the same thing, here to here, right? A multiple of one equation to the next thing until, right, I got to this one, right? And this one over here, actually, what I did is I multiplied throughout by a non-zero scalar, right? Which is -1, right? So I didn't swap anything, or I didn't add a multiple of I didn't, okay, so going from here to here, right? What I did is I didn't use something of type 3 or something of type 2. I didn't use something of type 3 or something of type 1, right? I used something of type 2, right? And what all of these going from here to here, you use an equation operation, right? And the equation operation doesn't change the solution set, right? So the solution set for this is the same as the solution set for this, same as this, same as this, same as this, and same as this, right? Which means that if you you thread your way back through the chain, right? This over here, solution set is the same as the solution set of this, right? Okay, and well, why do you go through all of this, right? Well, the strategy is that you're given a system over here, right? That seems difficult to solve, right? And it's stated over here, right? What you want to do is you want to transform your system by using equation operations. So you keep transforming in a systematic way until you get something that is the same in the sense that it has the same solutions, but now it's easier to solve, right? Okay, so that is, well, that's, I guess, the point about this lecture, right? The point about this lecture is you start with our original system and you systematically eliminate variables and so until you get something that is easier to solve. And the point is you want to make sure that when you are doing these changes, say like going from here to here, you didn't change the solution set, right? So what that means is that when you get to here, it means that the solution set is in fact the same as this, right? So if you solve this, that is effectively, well, that's literally the same as solving this over here, right? Okay, so your solution 2 minus 3, 4 for this over here would be the solution for this over here, right? Okay.